For thousands of years, humanity looked upward and believed the night sky represented something complete, an ordered, understandable system that framed existence itself. Ancient civilizations connected the stars into patterns and stories. To them, the sky was not empty space, but a meaningful structure filled with gods, symbols, and mythic forces. It was a ceiling of certainty, where everything above appeared fixed and eternal. As observation improved, those stories gradually shifted into measurement. Early astronomers began tracking planetary motion with increasing precision. They mapped cycles, predicted eclipses, and discovered that the heavens followed consistent mathematical rules rather than unpredictable divine behavior. Over time, belief in myth slowly transformed into belief in law. A new idea spread across cultures. Perhaps the universe was not shaped by stories, but by principles, rules that could be understood, calculated, and eventually mastered by human reasoning. That idea became the foundation of modern science. But history repeatedly shows a familiar pattern. Every time humanity constructs a model that feels complete, reality expands beyond it. Earth was once believed to be the center of everything, until it became one planet among many orbiting the Sun. The Sun was later thought to sit at the center of creation, until it was revealed to be only one star among billions within the Milky Way. And even the Milky Way itself eventually became just one galaxy among countless others scattered across an expanding universe. Each shift did not simply correct an error, it enlarged the scale of existence. The most profound change came when space itself was shown to be dynamic. When Edwin Hubble demonstrated that distant galaxies are moving away from us, the universe stopped being a static backdrop. It became something evolving, something with history. Space itself was stretching, carrying galaxies apart like points drawn on a surface that is continuously expanding. This single discovery changed cosmology forever. If the universe is expanding today, then in the past it must have been smaller, denser, and hotter. Following that logic backward led to a new origin model. Not an explosion within space, but an expansion of space itself from an extremely compact early state. This became known as the Big Bang framework. Later, another piece of evidence strengthened this picture. A faint, uniform glow was detected coming from all directions in space, the cosmic microwave background. It is now understood as leftover radiation from the early universe, a kind of ancient afterglow still traveling through the cosmos. At first, this seemed to bring clarity. But deeper measurements revealed something unexpected. The universe was not behaving entirely as predicted. Galaxies rotate in ways that visible matter alone cannot explain. Their outer regions move too quickly to remain bound by known gravitational influence. To resolve this, scientists introduced the idea of dark matter, an invisible form of mass that interacts gravitationally but does not emit light. Later, even more surprising data emerged. The expansion of the universe is not slowing down. It is accelerating. To explain this, researchers proposed another unseen component: dark energy, a mysterious influence driving space itself to expand faster over time. With each solution, something new became invisible. The more the universe is understood, the more it appears to depend on forces that cannot be directly observed. Modern space observatories have pushed this realization even further. Among them, the James Webb Space Telescope represents a major leap in capability. Positioned in deep space with a large, highly sensitive infrared mirror, it is designed to capture light that has been stretched across billions of years by cosmic expansion. This infrared capability is crucial because the oldest light in the universe arrives at Earth shifted into longer wavelengths after traveling across expanding space. In a sense, it allows astronomers to look deeper into time rather than just deeper into space. Earlier missions had already revealed how strange the universe becomes when viewed at extreme distances. One famous example came from the Hubble Space Telescope. It observed a tiny region of sky that initially appeared almost empty, so small that it seemed insignificant against the vast night sky. But after long exposure, that darkness transformed. What looked like emptiness was revealed to contain thousands of galaxies. Each faint point of light represented an entire system of stars, planets, and cosmic structure. What had appeared empty was actually densely populated with structure on unimaginable scales. This changed one of humanity's most basic assumptions. Space is not empty. It only appears empty because of distance and limited perception. With the arrival of more powerful instruments like James Webb, expectations were initially modest: clearer images, improved detail, and confirmation of existing theories. Instead, the results became more complex. Deep field observations revealed an unexpectedly large number of distant galaxies. More surprising still, some of these galaxies appeared far more developed than expected for their age. According to standard models, early galaxies should be small, chaotic, and still forming structure through gradual mergers over time. Yet some distant galaxies already show organized shapes, including spiral-like structures and well-defined mass distributions. This suggests that cosmic structure may have formed faster than current models predict. Additional spectral data revealed another surprise: traces of heavier elements such as carbon, oxygen, and nitrogen in very early galaxies. These elements require multiple generations of stars to form and spread. Their presence so early in cosmic history raises difficult questions about how quickly the first stars formed, lived, and died. These findings do not break modern cosmology, but they do stretch it. They suggest that current models may be incomplete in subtle but important ways. Beyond individual galaxies, these observatories also map the large-scale structure of the universe. What emerges is something known as the cosmic web. Rather than being randomly distributed, matter forms a vast interconnected network. Galaxies cluster along enormous filaments that stretch across hundreds of millions of light-years, while vast voids separate these structures. At intersections of these filaments, dense clusters of galaxies form, creating a vast cosmic architecture. This structure is shaped largely by dark matter. Although invisible, dark matter exerts gravitational influence that determines how galaxies form and move. It acts like an unseen framework, guiding the distribution of visible matter across the universe. Without it, galaxies would not maintain their observed motion, and large-scale structures would not remain stable. Still, questions remain about how exactly this structure formed so early and so efficiently. Some regions of the universe appear more evolved than expected, suggesting that either unknown processes influenced early formation or our understanding of cosmic evolution is still incomplete. Beyond galaxies, modern telescopes are also beginning to study planets orbiting distant stars. Through spectroscopy, they analyze how starlight passes through exoplanet atmospheres, revealing chemical signatures such as water vapor, methane, and carbon dioxide. This marks a major shift in exploration. Distant worlds are no longer just points of light. They are becoming measurable environments with identifiable chemistry. Each atmospheric reading provides a chemical fingerprint of a world we may never physically reach. And among these distant systems, some may even hold conditions suitable for life, though no direct evidence has yet been confirmed. Still, the ability to study such worlds from across light years fundamentally changes humanity's relationship with the cosmos. It transforms distant planets from imagination into data. What makes this era especially significant is not only what we are discovering, but what it represents. On a small rocky planet orbiting an ordinary star, a species has developed instruments capable of detecting light that began its journey near the birth of the universe. Photons that traveled for billions of years, crossing expanding space, passing through cosmic structures, surviving countless stellar lifetimes, finally reach detectors built by human intelligence. In that moment, time becomes connected. The distant past is not just reconstructed, it is directly observed. But perhaps the most important pattern is not what has been discovered, but what always follows discovery. Every time humanity builds a more powerful way of observing the universe, new surprises appear. Expectations are refined, then challenged again. Models improve, then expand. This cycle does not end. It continues with every advancement in technology and every increase in clarity. And so, through a golden instrument quietly positioned in deep space, that cycle continues once more, reminding us that the universe is not a completed structure waiting to be understood, but an unfolding reality still revealing itself across time and light.